Okay, let's continue. Yeah. Ready over there? Too tired. Stayed up until 3 a.m. Okay, so we're on to the last chapter, chapter number 3 of semester 1, which is electricity. If you can see it there, electricity. So the first thing we'll learn in this new chapter is something called current and charge. Maybe you know these words already, current and charge. So electricity chapter, final chapter. We have mechanics, materials, and now electricity. The 3 parts for semester 1. Right.
Hard time?
Huh?
Hard chapter?
I like it. Right. So from chemistry, or even just middle school, you know that you have this thing called electric charge, and it's a basic property of electrons, protons, and other particles. So you know from middle school that a proton, we say it has a positive charge, and an electron, we say it has a negative charge. And this is all basic stuff, which I hope you remember from chemistry. In fact, I think your chemistry teacher would be very upset if you didn't remember protons were positive and electrons were negative. And we know that things which are negatively charged and things that are positively charged, they attract each other. This makes electrons and protons stick together. So the electron is pulled towards the proton. And this is how we can form atoms. And things that have the same charge push each other away. Positive and positive push away, and negative push away. Repel is the word we use. And this is called the law of charges. You can just write something simple down like positive, positive, negative, negative repel, and positive, negative, they attract. Continue. Don't write the whole thing, just write what I said. Positive, positive, negative, negative, repel, positive, negative, attract. Continue. So, who said wait? Bruce? Okay. You're thinking you can make a skateboard. You're thinking, if I'm quick enough, he won't even notice. Right. Now, just on to some definitions. So, we say a current is a flow of charge. What I mean is, if we have a charge like a proton, and this proton moves from A to B, we say there's a current from A to B. So, this movement of positive charge, we say that's a current, that flows. So, that's all a current is, and you can write this down. An electric current is a flow of electric charge.
How many definitions does it?
OMG. There's not too many. There's about maybe 4 or 5 big definitions. Is that okay? Do you approve of this? Okay, you have this? So you know, in a metal, it's the free electrons that flow. You did this in chemistry. In a conductor, you have these free electrons, and here's a sort of a picture of it. So these are electricals moving in a wire. But I'm sure you've done this in chemistry. This picture? No? Draw the picture, please. It's just electrons moving in the conductor. That's how the current moves through the conductor. The electrons move.
What's the stationary electron?
Stationary electron?
No.
This guy, this
Yeah.
poor fella here who's not moving. Maybe he doesn't want to move. Maybe he's tired. I don't
It's
know.
not good?
Is it possible?
Yeah.
It's possible, but difficult. You drew this? Yeah? Got that? Continue? Okay. So, this isn't the only way the current can travel. So just before I go on, what exactly did you do in chemistry? So did you talk about the free electrons in a conductor? And did you talk about their movement? Yeah? No? Yes? And anyways, that's what a current is here. But you can also have this thing called an electrolyte. And an electrolyte is usually a liquid. I think it has to be a liquid maybe. It's a chemical that conducts current. Now, this is a little bit different to the metal, because in the metal, it's the electrons that move. But in an electrolyte, it's positive and negative ions that move. Now, you've done ions in chemistry. An ion is just an atom that has an extra or is missing an electron. Right? So you have positive ions, they are... Yeah. Oh, goodness. The positive ions are missing an electron, and the negative ions have an extra electron. So an electrolyte is a chemical liquid, and it's used actually in batteries to produce a current. And it's just a flow of ions, and ions are just atoms with extra electrons or missing electrons. And here's an example. I mean, you don't have to draw this picture. It's just something you might have seen in middle school. So an electrolyte is just the first sentence is enough. An electrolyte is a chemical that conducts electrical current. And maybe you also just want to say by moving ions. This makes it different to metal. So the ions move in this electrical liquid.
An ion moves in electrolyte?
Yeah, an electrolyte is usually a liquid where the current moves through it because ions move through it. Whereas with a metal, the current moves through it because only electrons move. So it's a small difference. It's worth noting. So can you see here in this picture, this here is a metal, this here is a metal, so only electrons move inside the metal. But this liquid is an electrolyte, so you can have positive and negative ions that are moving through it. Okay. Continue. Yep. So. Which way should we say the current flows? So here's a little picture of a battery. So should we say the current flows from positive to negative on the terminals here? Should we say the current goes from positive to negative? Or maybe we should say the current goes from negative to positive. So which is it?
It's negative, positive.
Negative, positive, positive, negative?
Negative, bad news.
The bad news, yeah. Both. So we have to be very clear with our English, okay? We have what's called the conventional current, or the normal current, or just current. And when we talk about that that one is always from positive to negative. But in fact, the electrons flow the other way. The actual electrons move from negative to positive. So be very careful. When I say current, or conventional current, I mean positive to negative. This is normally what we mean by current. However, often in the exam they try to trick students, and in the exam they might say, what is the current flow, or the electron flow? And that's actually opposite. So conventional current is positive to negative, electron flow is negative to positive. So, to be very clear, if an electron moves from A to B, which way do we say the current?
Conventional.
Yeah, which way do we say the conventional current flows, the current? Yeah, B to A, yes, B to A. Even though the electron moves from A to B, we say the current is actually from B to A.
What do you mean by conventional?
Conventional current, or just simply current. The meaning of current in the normal meaning. Another word for conventional is usual or typical. In other words, what I'm trying to say is, when we say current, we probably mean this, but you could stick in the word electron, and now all of a sudden we mean the other direction. So if I say, which way does the current flow? Well, normally it's this way, but if I said, which way does the electrons flow? It's the other way. Ah, yeah, that's the next slide. Yeah, getting excited now. We'll find out soon.
Is it happening at the same time?
Yeah.
Same time?
But this is a problem of English. So, what? Huh? It's the same thing. Yeah. So when I say the electron moves from me to you, I can say there is a current from me to you. No. Stop again. If an electron moves from me to you, I can say the electron flows from me to you, or there's a current from you to me. The same meaning.
But current contains charges, and charges are negative charges. So
I never said that.
yeah.
I never said. You know, it's my definition. I specifically never specified positive or negative. Yeah, you see. Now, there's a reason for all this bad English in a moment, which is coming up now. Continue. Yeah. So you might be thinking, why? For goodness sake, why can't they be the same thing? Well, we can thank Benjamin Franklin for that. The guy who used to fly kites in thunderstorms. You know, with the key at the end of the rope. You know this guy? Yeah. The problem is actually because we call electrons negative. This is actually the key reason why. And because we call protons positive. It would have been better the other way. If we called electrons positive and if we called protons negative, then this problem would disappear. Now you realize, and this is very important, it's not like the electron really is negative or the proton really is positive. These are just words we give to them to show that they're opposites. It's a bit like left and right. Left isn't really left and right isn't really right. If I swap the words, if I call this side right and this side left, and if everybody does that, there's no problem. Now everything will be fine. The same goes with positive and negative. If I call the electron positive and the proton negative, it doesn't matter, because opposites are still opposites, yeah? Likes are still likes, unlikes are still unlikes. They still, opposites attract, equal, the same, repel, so it doesn't matter. So it would have been better, because if it was this way, it means we could have said electron flow is the same as current flow, because electrons are positive and they move in the direction of the current. It's only because we call electrons negative. So Stephen Hawking talks about this in his book, how it's a pity we don't have the words the other way, because then it prevents this messiness here. And why are they the wrong way around? They're the wrong way around because Benjamin Franklin, when he was doing these experiments were done before people knew what protons and electrons were. So when he was doing this experiment, he said, okay, the charge here, I'll call this positive, and the charge left here, I'll call this negative. And it turns out, What he called negative was the plate that had extra electrons on it. So then it meant that the electron from after that would be called negative. But then only 100 years later did people realise, oh, actually, it would have been better the other way. But then it's too late to change.
Why don't they just change it?
Yeah, that's a good point. I really think it would be a good idea. But the only problem that this causes is for physics students learning physics for the first time. So there's not really a need to change it. You know? Do you get what I'm saying? Like, there's only one group of people that this causes a problem for. Physics students, the first time they're learning this. Other than that, there's no problems. You just have to remember it. Yeah. Anyways, that's life and that sucks, but that's the way it goes sometimes. Okay, so now, you know what you could do? You could start a Kickstarter campaign to get them swapped. Yeah, some kind of petition, online petition, you could have people sign up on. Yeah, come on, go for it. Go on, you can say, your campaign could be end the confusion, support swapping positive and negative. We'll have to think of something catchy for it. Okay, so how do we measure current? We measure current in something called amps. Maybe this is a word you've heard before, an amp. An amp or an ampere, because it's French. 1 amp of a current is, now, before you get the definition is very technical. The good news is, I've never seen this definition on the exam, but I need to give it to you. Formal definition. The amp is the current required that will produce a force of 2 × 10⁻⁷ newtons per meter between two straight lines that are parallel and perfect conductors and no cross-sectional area in a vacuum. Blah, blah, blah. So what do I mean by all of this? So we say that we have 1 amp of current moving through 2 conductors if, when they're a meter apart, we have this much force between them. Now this is a very technical definition, too technical for the exam, but it's the formal definition of what an amp is. So you have 1 amp if you have this much force between 1 amp of current. That's when you know you have an amp. Now, you okay?
Oh yeah.
Yeah, you sick?
I know.
Okay. This here, to give you an idea of how much an amp is, there's 13 amps of current in this. So this is 13 amps. Your USB charger, USB wire. Yeah, here. Or fell out. This one here, you could maybe get 2 amps current moving through this. This would be about 2 amps. This one here you could maybe do about 13 amps at most. The electric shower in your home, you could have an electric shower that could do up to 20 amps. So in your home you will never have more than 20 amps in a wire, and these are special wires. So 0 to 20 amps will be a typical value of current. Yeah. Continue? No? You should have the picture as well. Yeah, I know, it seems so ridiculous. Like, did somebody just pick this number one day? There's a reason for it being so particular, and it's complicated. I'm sorry to tell you this. What usually happens is there's a definition, and then the definition is no longer suitable, so then they have to change the definition, and then the new definition looks really really complicated when the original definition is quite simple, but maybe it wasn't scientific enough. I'll give you an example. It used to be that 1 kilogram, you could say like 1 kilogram is the mass of 1 litre of water. But then people realised, oh, that's not a good definition, because then do you mean salt water? Do you mean fresh water? Do you mean water at room temperature? Or water at 1 atmosphere? You know, so then you're like, oh, okay, so we need a different definition. I think something might have happened with this. I have a feeling that the original definition was something simpler, and then there was some change in what the definitions were to be more accurate, so it meant this definition then became messier. I think this is probably what happened. Yeah?
In a vacuum, that is force is to kind of sense of everything.
Yeah. Because if it wasn't a vacuum, the force would be actually a little bit less. So for the definition, it has to be placed in a vacuum. But again, this definition is just really a technical definition, and as some of you have noticed, it seems kind of like a fake definition that you would be so particular about the numbers. And really, I think what's happening is this definition needs to be like this to make other definitions easier. So the next definition we'll do is actually going to be quite easy because we have this definition done already. Next definition. Yeah. So the next definition is the Coulomb, and the Coulomb is what you use to measure charge. And the definition of the Coulomb is much easier now if we have the amp defined already. So the Coulomb, which is the letter C, and it's the standard SI unit of charge, and it's the charge you get when you have 1 amp for 1 second. So that's nice and simple. So if I show you here, if this has 1 amp, then if you connect this up to something and the current flows out, if you let the current flow out for 1 second when you have 1 amp, then the charge you have at the end, we call that 1 Coulomb of charge. So a Coulomb of charge is the total charge you get when 1 amp runs for 1 second. So that's now an easy definition. Now, so you know, this is, of all the definitions, this is one of the common ones in the exam. This is a common one in the exam.
Do you need to write the whole 2 sentences?
No, you don't even need to write the whole 2 sentences. You just even write the second sentence.
Is that right?
Yeah, please do, yeah. Alright, have you got that? So because of this definition, we can actually get a nice simple formula that relates current and charge. So we can say the total charge, or the charge that you gain, is equal to the current multiplied by the time. Where Q is the total charge, I is the current, and T is the time. Q equals IT. Got that? You may have seen this formula before, Q equals IT. No? I haven't studied physics before. All of this is new and exciting. Yeah. Continue? Yep. So, finally, how big is 1 Coulomb of charge? It's actually pretty big. If you have a Coulomb of charge, that is actually a lot of charge. And to help you see that, you should note that 1 electron has a charge of only minus 1.6 times 10 to the minus 19. So that means 1 coulomb is a lot of charged particles. A proton, the only difference with a proton is what? It's a plus instead of a minus. So if you have 1 coulomb, you must have a lot of electrons or a lot of protons. It's a lot. And in chemistry, you actually don't even write this down. What do you call a charge of an electron in chemistry? If you say this electron has a charge of, what do you say?
Minus 1.
Yeah, you just simply say E or minus 1. Actually, that should have said minus E. Let me fix that so I don't forget. So in chemistry, you would say an electron has a charge of minus 1. On your calculator, you have this constant called E, and E's value is this. Let me just stick in my minus. Oh, I did, but I never updated the file. Oh well. Anyways, can you write this value down? This is the charge of an electron. Now, be careful, there's 3 types of E on your calculator. It's the one that's on the lid, the constant. I think it's number 27 or 23? 27. Yeah?
No, 23.
Not on that calculator. On that calculator. Look, I have my calculator here. Look. Constant. No, not random number. 20 what? 23. So you see, my calculator has E built into it for the electron, rather minus E. So minus E is this. Yeah. Right, continue. So, yeah.
If we have like 1 coulomb and we have the charge, could we have the number of
Yep. If you had 1 coulomb and you divided it by this, then that's how many extra electrons you have, or no, sorry, how many electrons you're missing. Because if it has a positive charge, it's missing electrons. So let's actually see what that is. I don't need the minus. Oh. Anyways, it's a lot. It's a lot. So 1 coulomb means you're missing a lot of electrons. Yeah. Anyways, the point I'm trying to make is when we say that this is 13 amps, that's actually a lot for a unit. That you might think 13 is a small number. In this context, 13 is a big number. We often should be measuring coulombs in like millicoulombs and milliamps. This would be more normal. Right, a 100 milliamp current is flowing through a copper wire for 2 seconds. What is the total charge? Okay, can you calculate that using the formula? So what do we get? I don't really think you need the calculator. What's the answer? What is it? 0.2 watts. What's the unit? Coulombs. Yeah. Or in other words, 200 millicoulombs. Milliamp. So the answer is 200 millicoulombs. Is that okay?
Yeah.
Is it? By the way, if Q equals IT, then I equals Q over T. What's the unit for I? Amp. And what's the unit for Q? Coulomb. And T? Second. So in other words, 1 amp is the same as 1 coulomb per second. It's the same thing. And it's sometimes useful to remember that an amp is just a coulomb per second.
If it's the atom, yeah, right
No.
now.
Now, I've already thought about that because I thought that would be a much easier definition, but you can't have it both. So, for example, you have the way the definitions work is you can technically define the amp and then use this formula here to define the coulomb, which is what we did. Or what they used to do in the past, like maybe 40, 50 years ago, is first they began by defining the coulomb and then they defined the amp as a coulomb per second. But what's normal nowadays in physics is to first define what the amp is and then from that definition define what the coulomb is. It's the other way around now. So that's what they actually say in the syllabus, that the coulomb is defined from the amp. I don't know if this was different in your school.
That's the definition is not that long.
For what? The amp?
Yeah.
Was
They really like
an amp is 1 coulomb per second.
or something.
And then what's a coulomb then?
I don't know.
Okay, well anyways that won't work anymore. Okay. So it's quite an easy lesson, so there's only the one example. So just for a few minutes, if you can try these simple questions. Again with the face. You have like 5 minutes and then you're going home.
Just catch the bus.
Okay, how do we check what time the bus is for you?
What's the 49?
What?
49.
Yes, I can check any bus here. Excuse me.